Yes. So again, welcome to the Convolutional Neural Nets workshop, and let's begin with this question. That is, what is deep learning, right? So deep learning is a class of machine learning algorithms that uses multiple layers um, to extract or learn higher level features, right? The key word here is multiple layers, and as you can see that there are these multiple layers that are stacked up together, which kind of gives this network a deep sort of look, and that's where the name deep learning comes from. Um, so let's talk about some milestones and how CNN evolved over the years. So like many concepts, deep learning was also motivated from biology. It was motivated from the human brain, right? And we know that the human brain is the best processor out there, and it is natural to take an inspiration from the human brain um, to to build a computation model that can do classification, regression, object detection, and such tasks, which our human brain can do very easily and effortlessly, right? So in 1943, Walter Pitts and Warren McCulloch, they together designed this computational model that used threshold logic. This is basically nothing but an activation function, and they used it to build this computation model, and they called it the nervous net. So this was the beginning of deep learning. And let's talk about the evolution of backpropagation, right? So for those who didn't attend the last workshop, backpropagation is basically a way to calculate your gradients, and these gradients are used to update your weights, right? So in 1960, Henry J. Kelly, he um, he laid the foundation of backpropagation. So this guy actually created it, but at that time it was not very optimal, right? And Seppo in 1970, he actually optimized backpropagation. He also wrote a code in Fortran that you can actually code up and code it, but he did not use it in a neural net yet. And in 1985, Rumelhart, he finally used backpropagation in neural nets, and then since then it has become a common trend to use backpropagation in neural nets. Um, yeah. So in 1979, the first CNN model was built, and it was called Neocognitron. It was built by Kunihiko Fukushima from Tokyo in 1979. And like most of the networks at that time, he was also inspired by cells. And he mainly used this Neocognitron for handwritten character recognition and other pattern recognitions. And we'll go later into these slides, and we'll see that his network architecture looks very similar to the network architectures of today, that the CNN models of today, right? Um, and deep learning is such a field that requires a lot of computation power, right? And with a lot of computation power comes a lot of money. And but in the early 90s and before that, the computing power was not very good. So actually the computers could not get the best of deep learning approaches, right? And this actually led to a decline in funding for the DL society. But in the late 90s, there were like faster computers. There were And in 1999 there was the invention of GPUs, and GPUs stand for like graphical process units, and they are used for parallel computing, right? So they speed up your deep learning stuff by like over 1,000 times. Uh, SVM right now is like, it was launched in 1995. It is not a neural net, but it was like a competitor to neural net. So SVMs provided really good results. And the second thing they did, that they had very low computation. They didn't need a lot of computation power, right? So there was this general question out there, is that do we really need deep learning? Because given with like just 2 or 3% of improvement, but I'm training it for like 2 3 days or even 10 days for a very simple task. So do I really need deep learning? And but with the advent of GPUs, the computation time became actually comparable with the SVMs. There were a lot of inventions that took place between 1999 and 2012, but the most notable one was AlexNet in 2012, which was the first GPU implementation of CNNs, right? Um, so AlexNet won a lot of awards at its time. And in 2009, there was this image database called as ImageNet for classification. And the only difference, I mean, the major difference between ImageNet and other existing um, image databases was that ImageNet had high resolution images, right? And with high resolution images, you needed a lot of computation power. And as such, deep learning approaches require the lot of computation power for small images. So, so two two things that AlexNet did at his time that were revolutionary was that the first thing that Alex did was he used ReLU instead of Lineage, and the results were so good that the entire DL society actually stopped using Lineage after that. And the second was he used multiple GPUs for training. So this was the first time CNNs were trained on multiple GPUs too, and this gave him a good speed up, and he was able to do his computations within a day, right? And in 2011, 2012, he won a lot of competitions. And when we take a look at this figure here, these cuboids here are convolutions, and the ones at the end are fully connected layers. And we'll get into what these are later in the workshop. So let's quickly take a look at some good examples of where CNNs and how they are used. So the first application is object detection, and we'll take a look into YOLO. So YOLO stands for You Only Look Once. This was created by Joseph Redmond, and he's a PhD student here at UW itself, and he works with Dr. Ali Faradi. In fact, he's also taking a course in this winter quarter, and I also came to know that he's a pretty funny guy. So let's take a quick look at this video and see how like we'll not see into depth like how CNNs are used, but this is one application of CNNs. So basically, this was an application of how like these squares were drawn around objects, and it was actually objectifying like this is a car, right? This is a person, this is a truck, and basically this is object detection, and CNNs are used here. Sorry, let's take, yeah. The second thing is this is an application of GANs, but the basic blocks are CNNs again, and this is from a paper called Style Flow, and this is kind of really cool, and we'll take a look at how and what it does, right? So I'll just forward it to the cool part. Yeah. So basically, this is pretty cool, and this uses CNNs, but it also uses GANs, but the basic blocks are CNNs again. And let's take a look at another example. Um, sorry, yeah, the other example is sketching, right? So the input to your model is basically this terrible sketch, right? And it makes something so good. So this is again an application of GANs, but the building blocks are CNNs. And finally, let's take a look at this thing called as NERFI. This is another work done by Steven Seitz here at UW itself. He's a professor working in computer vision. And basically, this again uses CNNs. And I'll just get into the results part really quickly. So basically, you give it an input video and you get like a high resolution uh, um, video out of it. And this is pretty cool. And there are other applications of CNN as well, like super zoom and etc. So you can take a look like at what CNNs are used for. And also these slides will be shared with you after the presentation, so you can take a look at these videos in your leisure time. Um, right. So with that, let's move on to what CNNs are and how they actually function. Right. So I'll be handing it over to Sahil, and let's go forward.
Okay, so that was pretty cool. Now let's get more into the math and the structure of how we can design these things. So it'll slightly be involving, but if at any point you guys are not following along, just message in the chat, or you can stop me to clarify anything. So give me 1 second. Can you see this?
Yes.
Okay. Okay. So now can you all see my notes, or can you only see the slides?
Just the slides.
Okay, perfect. Okay, so I thought this was a really cool image of how we are like using the creation of Adam, but here we are creating the artificial intelligence, and we are kind of the gods creating that. So I thought that was pretty cool. And okay, so getting into this, in ANNs you have fully connected layers where each neuron in a layer is connected to the next one, like the one on the left. So as the size of the input increases in an ANN, the corresponding size of the hidden layers also increases in an exponential manner if you want to train the inputs in practical times to get pretty reasonable accuracies. So also ANNs are not specifically designed to tackle image data. So since, as we have seen last time, we always begin by flattening the images and feeding it to the ANN model. So as an example, if you have an image with 30 by 30 pixels, in terms of data, that's like 30 times 30 times 3 if it's an RGB image, and times 4 if you have like an RGB alpha format. So you can quickly realize how ANNs are not fit to train image data as they grow massively in size if you want to keep training them at reasonable accuracies. So alternatives is to use CNNs where we notably do not have fully connected layers. So an example of a CNN can be observed on the right. I think at this point, none of these really mean anything to you guys. So, but we can see like the close similarities between both the models. They both have like a feed forward thing where you begin with an image and you somehow do something to get the outputs. So this is what we'll be learning in the upcoming slides, where we learn how we can progress from one layer of the image to the other. So in so before we move on, I want to point out like one similarity. CNNs have alternatives to fully connected layers, but in some layers you can have like completely fully connected layers as well, which sometimes has shown to increase the efficiencies. So the overall idea is that we are using layers which are alternatives to fully connected layers like in ANN. So let's see the kinds of alternatives which we have. So primarily we have three different types of alternatives to the fully connected layers. The first and the most significant one is the convolutional filter, which is the signature of CNNs, and this is also what the name of CNNs comes from. So next, we'll also be looking into a bunch of pooling layers like the max pooling and the average pooling filters. Uh, you might not like the word filters might not make much sense, but I promise they'll make a lot of sense once we go into the next slides. We also have like a bunch of other filters like Gabor filters and deconvolutional filters and many more, which we'll be not getting into. But I just want you guys to be aware that there are alternatives to convolutions, max pooling and average pooling. So I really like this diff, which basically shows how CNNs work in the most compact way possible. So, so here we have the light blue image, and we can think of the filter as the dark blue shadow, which is being casted on the image. So a convolution is a dot product. It's an element-wise multiplication with the filter and a part of the image. So here we can see that there are 9 convolution operations which are happening. And since each convolution is a dot product, we'll have one number as an output. So since there are 9 convolutions, we have 9 outputs based on which the structure of the next layer is determined. So this newly generated like white filter is called as an activation map. So to put some numbers into what's happening, we can see an image represented by some pixel magnitude in the far left. And you have a filter, which is the one in the middle. And the next layer is obtained by iteratively taking dot products or element-wise multiplications and moving over the entire image. So this process of taking dot product between the filter and the input is called as a convolution. There are a couple of things to note. The weights in the filter at this point are learned by using backpropagation, very similar to how we did it in artificial neural networks. There we learned the weights of the connections, but in convolutional neural networks, we are essentially learning the weights of the filters. Um, However, it is not really essential to learn the backpropagation by heart, since most deep learning libraries do it for you in like one line of code. So as long as we have the intuition of backprop, we can train the weights if we know if we know the dimension of the filter which we want to use. We'll so a convolution converts the pixels in the respective values into a single value. So when we apply a convolution, we are essentially not only decreasing the size of the image, which is called as downsampling, but we are also bringing all the information in the field together into a single pixel. So we are evaluating chunks of or parts of image at one go, and we are coming at the new hidden layer. So let's see more on how these convolutional filters work. As an upcoming note, all the slides were taken from the deep learning class taken by Professor Ravikumar Bhattacharya at Mahindra Ekal Central, who taught me deep learning back in India. So these are all the slides from his class. And you can use these slides for reference, but I don't think they can be distributed. Anyway, okay, so let's begin with an image of size 32 by 32 pixels. And since each image has 3 channels, the RGB values, we have a data set which looks like 32 by 32 by 3, where it's the height, width, and the depth of the image. Now, let's say we have a filter with the size 5 by 5. It should be important to note that the depth of the filter has to match with the number of channels which we have in the input. So if we have 3 layers in the input, it makes sense to have 3 layers in the filter. So at this point, we really don't know. We are assuming that the filter's weights are already learned by backpropagation. So now I'll show what the feed forward operation would look like when we have all the weights of a filter already determined. So we'll basically be sliding over the image spatially, computing dot products like we have seen in the GIF. So the number of operations can be calculated as 5 into 5 into 3 for each convolution, and this will be sliding over the entire image. Now let's try to understand the size of the output image which we get from such a convolution based on the size of the input and the size of the filter. So so here when we convolve over or slide over all the spatial locations, we basically get a new layer, a new activation map, which will be of size 28 by 28 by 1. Since this is a dot product and we are doing it over all the channels, so they all basically compress into a single dimension. So this is for one filter. So this is for, let's call it the blue filter. We can have as many number of filters as we want. So let's say we have a second green filter, then we get a new activation map with the same dimensions, but this will essentially be capturing different features of the input image. So if you have like 6 different filters, then you'll be capturing 6 layers or 6 different features of this image, and you can stack them together to get activation maps of the dimension 6. So this is a really interesting thing to think of. These are essentially new representations of the same image, where instead of RGB values, we are denoting them in a much more smaller yet deeper representation, which is made up of the image features, which I think is really interesting. So this is essentially deconstructing the image into the features which make up the image. This is also really cool if you are working with fluids and you want to see how you can model decompose and observe the modes of the flow or multi-scale phenomenon like advection or turbulence. So, so overall, you basically have a structure of a CNN which might look something like this. So to reiterate what we've been learning so far, in the first operation, you begin with say 6 filters and you arrive at a layer which has a depth of 6. So if you have 6 filters, you come up with 6 activation maps. So the first layer essentially has 6 in the depth. So now if we have 10 more 10 more filters like in the next layer, you'll have 10 as the depth of the next layer. Also, you can see that the size is gradually decreasing from 32 to 28 to 24, but the depth is more or less governed by the number of filters which you are having in between each layer. So now let's try to see the exact formula, or like in this slide we had like how do you go from 32 to 28 when we know that we have a 5 by 5 filter. So this is basically the formula which you use. It's if n is the size of the input and f is the size of the filter, and I'll get into what stride means in a minute. So previously we had n as 32 and f as 5 because we had a 32 by 32 image and a 5 by 5 filter. So stride is essentially the number of pixels we are moving at a single time. So far in all the GIFs and all the examples we've seen, we were only moving with a single stride. So stride is equal to 1. So this formula essentially boils down to n minus f plus 1. So in this example, we have a sample with, say we have n is 7 and f is 3. So if we are applying a 3 by 3 filter on a 7 by 7 image, we get an activation map with a size 5 by 5 and so on when the stride changes. So next,
Sahil, just a minute. Can you take a quick look at the chat? There's this one question about fluids. I think you'll be able to answer that better.
okay, one sec.
Yeah, sorry for interrupting.
Uh, okay, can you guys still see my screen?
We can see your screen. Yeah, we can
Just
see
a
the
tiny. Oh no, it's back. Yeah.
Okay, yeah, I'm just having some problem. Okay, for fluids, will this get very expensive because all the scales interact with each other? It's actually a really interesting thing since the expensive or the number of operations don't really change. But I think if you want to get higher accuracy of the modes which you have, or if you want to have modes which are rich in features, it will definitely be more expensive to capture them. So I personally use CNNs to just get a sense of the dominant modes and see how they are like different from POD modes or PCA. Okay, so can you explain stride again? Okay, I totally can. So can you still see my screen?
Yeah.
Okay. Okay. Wait, is that cool? Okay. Okay, can you see my comments?
No.
Okay, that's awesome. So in this GIF, we are essentially moving the shadow. We are moving the filter, which is like in a dark blue thing. We are moving it. We are just displacing it by 1 pixel at a time, right? So it's going from the first 3 by 3 chunk to the next 3 by 3 chunk. I'll get into what a stride of 2 would look like in a couple of slides, but does this give you like some intuition on what a stride is doing? So in the first iteration, we basically are starting at the 0, 0th pixel, and in the next iteration, we are starting at the 0, 1th pixel, and so on. So if the stride were like 2, then we would start at 0, 0 and then move to 0, 2. So it's just the number of pixels by which you are displacing in the next operation. So does that like give a sense on what stride is doing?
Yeah, thanks.
Okay. Yeah, it makes sense, right? So if the stride is like longer, we'll essentially do like lesser number of operations. So we'll only have n minus f by a bigger number. So the total number of operations would be reduced. So the size of the activation map would also be reduced. Okay, so this is what an overall structure of a CNN might look like. Uh, you could have an activation function after you get the activation map, like you could add a ReLU or you could add TANH or whatever to get the activation values in the activation map. So if you apply this stride, if you apply this formula of n minus f plus 1, you can see that n is 32, f is 5, so n minus f plus 1 is basically 28, and then again we have a 5 by 5 pixel, so 28 minus 5 plus 1, so this is 24, and so on. So that is how the size of the layers can be calculated beforehand. So let's see the other types of alternatives to fully connected layers which we have. So so we've seen the convolutional filters. Now let's see pooling layers. So notably like max pooling and average pooling. So in the first example, let's check out what max pooling does. So it is a really simple layer that does not require any data to be trained. So a max pooling is a fixed operation where you have you have an input image of, let's say, size 4 by 4. So here, as John asked, like we can use a stride of 2. So if we have a stride of 2, our formula essentially becomes 4 minus 2 by 2 plus 1 if we have a filter of size 2 by 2. So far, if stride was only 1, like after calculating this part, we would go to this part of the image. But since stride is 2, we are skipping 2 pixels at a time, and we are essentially calculating the blue part of the image first, and then we are moving on to the green part. So here stride is 2. And so what does max pooling specifically do? It basically takes a look at all the images in the all the magnitudes in the part of the image which we are focusing on. So if we are looking at the blue part, it will basically calculate the maximum value. So here this is 9, and we just replace with that value in the output. So in the green part, we have the maximum value of 7. So in the output, we have 7. And here it's 8 and 6 and so on. So this is basically what max pooling does. It, instead of doing convolutions or dot products, if we set the size of the filter based on this formula, it gives us an activation map by only choosing the maximum values. This is not considered as a hidden layer. This is usually added as an addition to a convolutional layer, and this has shown to really improve the results. So similarly, let's have a look at the average pooling layer. This is exactly what max pooling does, but instead of taking the maximum value, it basically gives the average value in the output. So that's super intuitive. And again, we have this formula which basically says the dimensions of the output activation map. So now I think this is the most interesting feature of convolutional neural networks. So this will also touch into what I meant by using CNNs for model decompositions. So now that we have understood the different layers that we have, I'll try to give an intuition on what the layers are essentially doing. So let's have a look at the bottom of the image. So this is an example convolutional neural network, like, and we are feeding it with a bunch of images. So these images are faces of people. So we have one convolutional layer, and then we have an activation function, and oh no, so this is essentially, so these are essentially the filters which we have, and the weights of the filters are being learned by backpropagation or any weight optimization method. So once we have these filters, we have an activation map which we get, and then we'll basically going over and adding a bunch of filters, and then we'll get some more operations. And so these are essentially the filters which we are trying to learn using backpropagation. So as you can see, so these are, if we try to plot the weights of the filters, we can see that the first layer of filters which we learn might look something like this. And as we go deeper into the network, the second layer might look something like this. And the final layer might look something like this. So the first layer, if we have a deeper look into it, is essentially capturing the edges or the sharp features of the images. And as we go deeper, it's starting to identify bigger parts of the faces which are more coherent in nature. So going from sharp outlines, it is starting to directly identify, say, eyes or nose. And if we go even deeper, it's directly forming an idea on what the different types of facial structures might be. So there is a really interesting paper on eigenfaces. So this is essentially learning the in air quotes the modes of different facial structures. And when you try to predict things, it will essentially try to see which mode of the learned structure is the input most similar to, and then based on this approximation, it will try to predict the closest class of the face which it will belong to. Okay, so that was a really in-depth analysis on what the layers are essentially doing. So it is also important to point out that the more deeper your network is, the more gradually you can learn these features, and the more accurate your results might be. So if you have a really narrow layer, the propagation from like sharp features to coherent parts of the face to faces might be abrupt, and this might lead to stability issues which might cause like decrease in the accuracy. So the takeaway is have like deeper networks and have like smaller learning rates and so on. Okay, so if instead of feeding in the facial data sets, if we feed say like multi-scale turbulent data, these might be the so each block or each filter might represent the dominant mode of evolution in turbulence. So now that we know the different kinds of layers or the filters which we have in a CNN, let's have a look at the most popular cases of CNNs and see, or the most successful models of CNNs which are like really well received by the deep learning community, and see if they make sense to us from what we have learned so far based on the convolutions and max pooling and so on. So this first architecture was proposed by Jan LeCun back in 1998. So he's considered one of the founding members and the most important researcher, one of the most important researchers in deep learning. So this is the network which he proposed. So I think we can try to make sense of what's happening in this more or less. So he's beginning with an input image, and he's basically doing a bunch of convolutions, and he's getting a bunch of activation maps. He's calling them feature maps. So now we do subsampling. Subsampling is essentially either max pooling or average pooling. So in this case, it refers to max pooling. And using that, you get a bunch more layers, and then you do convolutions, you do max pooling, and then you are adding fully connected layers again in a CNN. So as I said in the starting of the talk, you could have like fully connected layers in CNNs, as they are known to give really good accuracies if you place them right before the outputs. And he finishes with something called Gaussian connections. So uh, let's look into so this network was really popular. It basically showed how deep learning can be useful. It showed incredible results and all those good things. And now let's take a look at one more popular network which Alrick mentioned in the first part of the session, the AlexNet. So every couple of decades there are like a few scientific personalities who are like so attractive that they just draw you into their research, like how Marie Curie inspired like a whole new wave of female scientists, or how Richard Feynman inspired like a whole generation of physicists, and so on. So along those lines, the work of Alex Krzyzewski is one of the most uh, significant models which inspired like a wave of deep learning researchers and deep learning students. So he's also one of the most cited researchers in the 21st century. And he proposed the AlexNet back when he was a PhD student. And his paper currently has like over 75,000 citations. And there are many researchers whose entire careers don't add up to that. So So this is a really significant work in computer science. He's also the co-author on Dropout, which we were learning in the last session. So he's a really influential guy in artificial intelligence. So this is basically a deconstructed view of what an AlexNet does. This is what Alrick was showing you guys in the first part. So he proposed it back in 2018. So this has 8 convolutional layers and 3 fully connected layers. As you can see, there is a convolutional network with a bunch of filters, and then you're doing max pooling and then convolution and max pooling and so on. And you finish with a softmax, because he essentially developed this model for a image classification dataset. So now let's explore some literature on CNNs and how they are relevant to us as mechanical engineering researchers. So in this work by Fukami et al., which came out in 2019, they implement super resolution in fluids using a technique called hybrid downsampled skip connection multiscale network. It is inspired by traditional convolutional neural networks, and this is one of the most fastest growing research on super resolution for turbulent datasets, and it already has over 100 citations in the last year. So also being a fluids researcher, the last time I've been overly biased towards showing you guys research in fluids and only showing you examples of ANNs which were used in fluids. So this time I hope to diversify and expose how CNNs are used in other predominant mechanical engineering disciplines. So let's take an example for researchers in energy or power control. In this paper by Lee et al. Written in 2018, an approach for deep power control is presented, that is DPC. This in DPC, the transmit power control strategy to maximize either the spectral efficiency or energy efficiency is learned by means of a CNN. And in material structure and design, I want to point out this paper by Season et al. That came out in early 2018. This paper is really interesting. It develops an objective data-driven approach to efficiently and accurately link a three-dimensional microstructure to the properties of this microstructure. And CNNs are used to learn the most important features of the structures, as we have seen in what the convolutional filters learn. And finally, Alec did point out to a bunch of interesting examples in computer vision, which are heavily used in robotics and self-driving cars. So this is another example in robotics, which is used for improving pattern recognition, and which is used by learning pattern recognition algorithms using CNNs. So in this paper, they present a novel robotic grasp detection system that predicts the best grasping pose of a parallel plate robotic gripper for novel objects. So this is also done using the RGB and alpha values of an image from the scene. So finally, here are a few references, and I've added references to the background and the starting image which I used, and going back to the resources which you guys should check out. This is a CNN video by Deep Lizard, which goes into more on the what the filters are learning, and it's like an 8-minute video, so you guys should totally check this out. And finally, there is the classic course on convolutional neural networks by Andrew Ng. He's like, his works have been cited like over 100,000 times. He's one of the biggest names in CNNs, and he has this course available for free. So if any of you guys want to properly go into uh, like what convolutions are intuitively doing or what max pooling does, you guys should totally check out this course. And finally, this is the course website for CS231 on CNNs by Stanford University, which has like the material to understand the theory behind CNNs. So now let's actually begin our programming session, which which is interactive. So you guys should totally follow along and try to program it with me if you can. So okay. Okay, so can you guys see this?
Yes.
Okay, so is any one of you like have you guys, so okay, so how many of you guys have worked with Collab before? Did anyone do that? Okay. Okay. Okay, so it's nothing fancy. Just go and click on Google Colab. Just click on the first link which comes up, and you will have a notebook which will look something like this. And once you have a notebook open, just let me know, and we'll begin the programming session. So you guys should totally open this, and we'll actually program like the whole neural network from scratch. So you guys should definitely follow along, and just go to google.collab and just click on the first link. I think you have to sign in, and just click on create new notebook, and you should come to this page. You don't have to install anything. It's just an online thing which also gives you some GPU support, so that's pretty cool. Okay, so is everybody ready? Would anyone like to take like a couple of minutes to get started on this page? Or does anyone need any help with opening Collab? Because I think it will really help you guys if you are like following this along instead of just looking at the code and me typing. So, okay, so I guess everybody is on page, and okay, so let's program our CNN. Oh, to be more precise, so in the first part of the I'll actually we actually had a lot of feedback saying uh, there wasn't enough coding the last time. So since we'll be building on how you begin with an ANN, I think it's better if I just begin with how you can build an ANN, and then we can move on to and then Alrick will take over and he'll say how you guys can build a CNN. Okay. So these are all just the comments for me to like remind me what I'm supposed to do. So first we'll begin by importing TensorFlow as TF. So if at any point like you guys don't understand what I'm doing, just I do have the chat open this time so I can see what you guys are typing. So can you guys see me typing, like, or is this gone?
Yeah,
Yes,
I can see it.
Okay, so first we'll begin by importing TensorFlow because that's what we'll be building our model. So this way we don't have to do anything from scratch. So next we'll import NumPy since we want to do a bunch of operations on the data before we throw it to TensorFlow. Next we'll also import matplotlib.pyplot as PLT. So this is essentially used to plot your results and see how your models are doing and so on. And then we'll import time to have a sense of how fast things are happening. So now we have written some code. If you want to run this thing, we go to this button and we click on the triangle. So if you are doing things in a fast-paced manner, it's good to have this shortcut where if you have like say like print something, you can So you essentially type this thing and you enter like shift and enter. So that basically runs the cell instead of moving the cursor and then writing things, which is boring, I guess. So, so here we'll again have an example of an image processing example. So we'll be starting with a data set called Fashion MNIST. So this is a data set which has a bunch of articles of clothing, bags, shoes, whatever. And we'll be training the, so there are like 70,000 images of these clothes and articles of clothing. And these are all labeled. So you have images and you have labels. And we are using this to train our model to learn the classification problem. So since we are in a workshop, we don't want to download any new data sets. So the module TensorFlow has a module called Keras, which has data sets, which has Fashion MNIST. So Fashion MNIST is a data set which is preloaded in the TensorFlow environment. So this is, so we want to okay, so if I run this thing, it will basically, it might say downloading for you guys since you are doing it for the first time, and it doesn't say that since I've already downloaded mine. And so once you have the data set, you essentially, this data comes in the format of train images and train labels and test images and test labels is equal to Fashion MNIST. So does anyone have, okay, so basically Fashion MNIST has 4 objects. It returns 4 objects, and we are saying treat the first object as train labels and train images, and the second object as train labels and train test images and test labels and so on. So this is just the inherent structure in which Fashion MNIST is like preloaded into this module. So these are all basic stuff, and there's nothing really happening on a deeper level. So so after I execute this, I essentially have um, oh, okay, there's actually a loading command. So if we have an object, I also have to say load data. This has a bunch of other features, but we want to load data at this point. So we are essentially saying like load data from Fashion MNIST and label them as train images, train labels, test images, and test labels. So testing data we'll use for testing the model after we are trained, after we are done with the training. So initially we'll only focus on the train images and train labels for now. So now I also want to point out to the different classes that we have. So so this step is optional, like you don't have to type these things. I just wanted to mention this for clarity. So so in train labels, we essentially have, so the data set has 10 different categories. So all the images belong to one of the category, which is like listed here. So they could be, it could be a t-shirt, it could be a trouser, a pullover, a dress, a coat, a sandal, a shirt, sneaker, bag, and an ankle boot. So each of the 70,000 images in the Fashion MNIST dataset belongs to one of these classes. So let me also run this. You don't have to type this thing out. I'm just doing it for clarity. So to get like a better understanding on what we are dealing with, let's try to plot an image in the Fashion MNIST and see like what we have. So let's take the first image. Indices in Python start with 0. So we'll just say train images of 0. This gives you the first image. And now I'm saying, now I'm using the PLT module, which is matplotlib.pyplot. And IM show essentially means show me the image. It's saying like image show. And we also want to plot the magnitude of the image. So we'll just say pld.color bar basically shows you the color bar. Okay. So now it's saying that the first image looks something like this, and the magnitudes are varying from 0 to 250. Okay. So also let's see what the labels are. So this is like the first image. So let's see what the label corresponding to it is. So we can say train labels of 0. So it's saying that the label corresponding to this image is 9. So if we check into this, so since there are 10 categories and Python starts from 0, a 9 would correspond to the last one. So this is an ankle boot. I guess that's how ankle boots look. And okay, so now we have a sense of what training images and training labels are. So in this data set, training images are basically images like this, which are stacked over on the top of one another. And training labels are the corresponding categories to which they belong, and so on. Okay, so it is always a good idea to scale your images to 255. So here you can see that the images are varying in magnitude from 0 to 255. So when we do this, and let's also do the same thing for test images. So once you execute this cell, now the magnitudes should essentially be varying between 0 and 1. This is just better since the activation functions are working on the assumption that the inputs vary from 0 to 1. Also, reducing the size from reducing the range from 0 to 255 and 0 to 1 doesn't really change the structure of the images, which we can see when I execute this. So this cell is executed after I execute this cell. So all the magnitudes are correspondingly like mapped. So as you can see, the mapping is from 0 to 1, and it more or less has the same structure. So we're good to go. So now let's start building the model. Let's actually build our ANN. So let's call it model ANN, and let's begin with the TensorFlow module, and we'll go to Keras. And in Keras, we have this thing called sequential. Sequential essentially means that we are adding a bunch of layers which are in a sequential order. Or so this is just some syntax which you have to follow to code things up. You begin with these closed brackets, then you have square brackets, and then you can say tf dot keras dot layers dot flatten. So flatten essentially takes the, so okay, let me just write the whole thing and then I'll get into what they mean. So we know that the pixel size is 28 by 28. So I'm saying the input size is 28, 28. Okay, so this line essentially means add a layer in Keras or add a layer in the sequential ANN model, and the input shape is 28 by 28 pixels, and I'm asking you to flatten the image. So you have a 2 by 2 image. So you have a 2-dimensional image, and flatten essentially converts it to a 1-dimensional array. Now let's add a hidden layer. So this is, keep in mind, an artificial neural network and not a convolutional neural network. So let's just add dot keras, and let's add a layer, and let's add a hidden layer. So hidden layer is a fully connected layer, and let's say we have 128 neurons in the hidden layer, and we want to have a ReLU activation function. So dense essentially means that it's a fully connected layer. So this is our input layer and this is our hidden layer. And we'll just end with the output layer. So this is also a fully connected layer, and we know that there are 10 categories in this data set, so we'll just say the output is 10. Okay, so that's it. That's our ANN. If we run that cell, okay, so let's see what's wrong. Oh yeah, I have to add a comma after each one. Yeah, it wouldn't mean much. Image shape. Okay, so this is actually the input shape and not the. Okay, everything is running perfectly. So we specify the input shape, the size of the input. We have a hidden layer and we have an output, and that's it. We built our model, and we are good to go. So now we want to add a loss function. So we can add a loss function where we can compile the model. So just like how you would compile a programming language, you would add. So when you're compiling, you say the superficial things which you want to add to which you want to. Okay. So while compiling the model, you can specify the loss function, which the model is essentially trying to reduce. So optimizer is okay. So an atom as an optimizer is the most common one, and the most important thing is the loss function. So we'll have a loss function in keras, losses dot sparse, and okay. So okay, so this is how you would compile a model in. So this is how you compile the ANN. You begin by specifying the optimizer, which means adaptive movement estimation. And the most important thing, you want to have a loss function. So our ANN during the training process essentially finds these weights, which essentially reduce the loss value. But the loss values might not always be intuitive to understand. So we have a metric called accuracy. So metric is essentially, the metric is not part of the training process. The loss is only the part of the training process. So as the loss is decreased, we can say, show me a metric of accuracy using which I can understand like how well the model is performing in the training. ACCU.
There's an
Okay,
extra bracket near loss, I guess. Yeah, that's it.
yeah.
The extra closing bracket near loss.
Okay, I guess this one went over there. Okay, so now you have compiled the model, you have specified the loss, you have specified the accuracy. So you can just say, so this is just for like knowing how long your training is taking. So you just say, so you say you begin with a time.time, you say model.ann dot fit. So fit essentially begins the training process, and you say, so train using training images and training labels, and train it for 10 epochs. So basically for 10 iterations. So end time, like time.time, and so this is just to get a sense of the time it took to evaluate. So the first and the last comments are irrelevant, and the middle comment basically does the training. So you're saying, so this is the model which you built. You're saying fit, which means train or fit the images and labels to learn the weight. So when you just run this thing, it basically shows you the loss and how it's evolving over time. And you can see the accuracies as well. So the first accuracy is always like, it might not always be an accurate measurement of how the training progresses. So, but you can see that the accuracy begins to fall as more and more epochs are getting trained. Okay, so by the end of 10 epochs, we have like, it's actually surprisingly good accuracy, and we have like 10% accuracy. Okay, so accuracy, essentially we want higher accuracies. So the only trend which we should notice is that the loss values would decrease. So the objective function which we want to minimize is decreasing, and the accuracy of the model is increasing. So it went up to like 12% accuracy, which is, I don't know, I think like really terrible. So okay, anyway, let's see how we learn more on how we can increase the accuracy, like once we begin building the CNN. So now let's just see how the function did. So we have already trained the model. So now let's evaluate like how well it's doing using the testing data. So you just say model ANN dot evaluate, and evaluate the model on test images and test labels. So this verbose is equal to 2 essentially means show me the outputs in like the second mode. These are all like various options which you have in Keras. So that's in test function callback. So okay, so this is test labels. Okay, so this is the measurements on the training data, and these are the measurements on the testing data. So on the testing data, you see that you have like a 12% accuracy. So now let's see how, now that you have trained your model, let's see how you can use your trained model to predict something. So to say like tf.keras.sequential. So you're essentially building a new ANN model on the top of your already existing model, but in the end, you are essentially adding like a softmax function. So the measurements would still be the same, but softmax just gives the outputs in a much more readable way. So now you have a new ANN model, which we just we are using the older model, and we added the softmax function. And so now let's have an image from the test images. So let's see what the first image would look like. So in the test images, the first image looks like that, and we know that we can see like what it's actually supposed to mean. If we check the test labels, so it says it's a 9, which is an ankle boot. So let's see what our model predicts. So if we have an image, this is how you would predict it. So we have this probability model, which we just built using a sequential model, and so we just say predict, and we give it the test images. So when we are predicting, we don't have an idea on what the test labels might be. So there are no other inputs into the prediction. So once you run this, you have probabilities of all the test images, and so we know that the first image is an ankle boot, and let's see what the ANN is predicting for the first image. So these are the outputs which our ANN is giving. And so these are basically the probabilities of belonging to a certain class. So it says it's like a 1.2% of belonging to this class and like 17% of belonging to this class and so on. So since the accuracies are really low, the correct class, it's only showing that it's identifying this with like 14% accuracy. So, okay. So to see the exact class, we can also say like class names of np.argmax of, oh yeah, like you guys should actually do much better. It should actually be like 80% or something. So this was really stupid. I don't know why it's going like that. That was actually one of the points. Like even if it's like just one shallow layer, it should be like way better than like I don't know, like 15% accuracy. Yeah. NP dot max. Okay. Anyway, so you basically understand like what's happening. You can see the range of probabilities which you get from predictions. So now Alrick will take over and he'll say how you guys can build a CNN and see how the accuracies change in that case. So Alrick, are you ready?
Yeah. Let me just quickly share my screen. So basically, yeah. So I've kind of run the previous model, and yeah. So let's try and code up the CNNs. Right. So what I'm initially doing is, okay, first you guys have reached till this point, right? Because it'll be good if we are coding together. Um, so initially I'm just getting all the libraries out, all the functions that I'll be using. So if you guys can just quickly write this down. I just had it earlier because I didn't want to forget some. Right. So the first important thing that we need to do to design a CNN model is we need to know the shape of our model, right? Shape of our input, sorry. So let's do that pretty quickly. So, right. So we'll do that and oh my bad. I think we'll have to run the other ones, but it's okay. It should not take much time. Done before. Okay, we just wait for a little time so that it finishes running. So
It'll be
basically,
cool to see the accuracies like and see if it's still higher or
no, the accuracy will be higher. I think I know
see.
what happened was I think you didn't pass this argument and you're
Oh,
lost.
I was
So
actually gonna say from
yeah,
logics is equal to true actually does I think the
so
scheme is more stable or something. I forgot to add that part.
what
Okay.
happens in from logis, it adds a last softmax layer because you're not adding here. So in fact, if you had done something like activation equals softmax here, then you would not require this thing logits, which I'll exactly be doing in CNNs. But basically, you're supposed to get like good accuracy, like around 87, 91
Yeah.
with simple ANNs. But okay, no problem. We'll move forward. We'll do CNNs. So this is the shape of our training images. This is basically 60,000 images, and your height of the image is 28, width of the image is 28, and similarly for test we have 10,000 images. And now that we know the shape of our image, let's of our image of our data, let's move forward. So one thing missing, you must be realizing that when we did the workshop, is that we also had something called as channels, right? So here, because we are dealing with grayscale images, our channels are like 1, and that's why it doesn't show in the data. But while actually feeding our input to the model, we'll have to add that one dimension, which we'll do later on. But first, let's start with designing a model. So I'm kind of making this as a sequential model. So basically, when I say it's a sequential, it's nothing but like a list. So what I'm going to do is when I do something like dot add, so basically I'm just adding something to it. So this will be now A. So if I add A, so this will be A. If I add B, then this will be basically B. So it will be in a particular order, right? And the first thing that we want to do is we want to add an con 2D layer. Okay, so cn to add con 2D, right? Now we're going to specify some parameters. The first is filters. So what we're going to do is from one channel that we have one channel because it's a grayscale image, we're going to convert this from 1 to 32. And what we're going to do is we're going to keep kernel size as 3,3, right? Uh, you don't need to specify strides in this case because so we'll specify we want 1,1. That means that is actually the default value, so you don't need to specify it, but we'll do it for the first time. And the important part here is input shape, right? So we're going to give the model some detail about the input shape, and the input shape is supposed to be 28,28,1. Remember the missing one that we will later add in our training images, but for now we'll do this. And the next thing I want to add to my model is an activation, right? Activation and ReLU. So we're going to use a ReLU activation, and after an activation, we're going to use max pool. Max pooling. Oh man, okay, sorry, 2D, and we are going to give it the pool size to be 2,2, right? So it's going to do a max pool over like um, a matrix of 2,2, right? So basically this is it. This is you can imagine this as your one block, right? And now what I'm going to do is I'm going to call this block 1, and I'm simply going to copy this. I'm going to copy this, and for now we'll not go deeper because we are not using a GPU, so it might take a lot of time. But let's change 32 to 64. So now, so what we'll do is we'll first visualize what is our output shape right now, right? So we want to know that it's good to know what your output shape is so that you can design models better, right? So let's just run this pretty quick. Oh, output shape, my bad. Right, so none is currently batch size, so you don't need to worry about that because the model doesn't know about the batch size yet. But basically what is going to happen is a model of 28, a training image of 28, 28,1 is going to be passed to the first block, and the output of that block is going to have a shape like 13, 30, 32. 32 as we specified, and as you know that when we apply convolutions and max pool, we are actually shrinking our image. So that is correct. So our height and width have both reduced from 28 to 13. Now I'm going to comment this, and what I'm going to, okay, wait. Before commenting, I just want to see how our model looks, how our model output looks after the second block, right? Um, and now it looks like something is 5,5,64. That's enough, I think. We can now use fully connected layers and do the further analysis, right? Fully connected layers. So the first thing we want to do is we want to flatten our data. So what I mean by flatten is like, okay, so basically cnn dot add flatten. So what would flatten do? It would do something like this. So suppose your data is something like batch one. Your data is of shape batch, comma y1, comma y2, right? So what would data do? What would flatten do? It would convert this into something like y1 times y2. So what it does, it keeps the first dimension as the same as the way it is, and then it would just bring up all the dimensions together. So if we simply print out the shape again, we print out the shape again, it'll be nothing but 5 times 5 times 64, like, which is 1600. That's good. Now let's move on. The next thing we want to do is we want to add dense layers, right? So what we'll do is we'll convert 1600 to 64 um, using a dense layer, and we'll also add an activation. We'll add the activation reload. So the other thing we'll do is we'll add this again, okay? Because remember that we finally need 10 outputs because we have 10 labels, right? So, but actually before that, let me just quickly add this dropout, right? So dropout is basically what I'm saying is that with point to probability, for each element it has point to probability of being converted to 0. So dropout is one of those techniques in which you reduce overfitting, and because CNNs have so many parameters, it's good to use some regularization, or as we call, like, anti-overfitting techniques, and dropout is one of those, right? So next thing I'll do is I'll just add another dense layer to output a total of 10 classes. And so the one thing the one thing that Sahil did not do was add activation softmax, and that's what you're going to do. So what it's going to do is going to give you a probability distribution over these 10 classes. So basically what we will be doing is we'll see the class with the highest probability, and we'll say that that is our prediction. And all right, so what we could do is now we'll compile our model, right? And we'll use the optimizer Adam. Adam is one of the best optimizers out there. So it's good. It's okay if you can use Adam for all your networks. The second thing, we'll use the same laws as Sahil has used, so that we can actually have a better comparison. And in our case, since we have already used the softmax function, we'll say that we don't want logits, right? And finally, we also want the metrics, which is basically accuracy. Yeah, and we are done with the model compilation. So let's just run this block really quick, see if there are any errors. Model CCN, oh no. Oh, okay, yeah. So that's good. So we have no errors till now. And basically we have a block 1, we have a block 2. We could add many such blocks, but it will give you higher accuracies for sure, but for now it's just a workshop, and you should definitely try that later on. So one quick thing what we'll do here is we'll take a look at the summary of the model. So we can see that our first conv layer has 320 parameters. This is our shape, and this really gives you a good outlook of how your model will actually do the training, right? And then, as we discussed earlier, that we need this one channel here because our input shape is 28, 28, 1. We'll just reshape our train images, right? So what I'm doing is the shape of 0 is nothing but the batch size. So I want to keep batch size the same. And then I'm just going to do this. So I'm just adding this one external one here, which is pretty important. And yeah, we'll be using this. So yeah, and then test images is basically just changing everything to test images, right? And then finally, let's look at the shape of our train and test images. Uh, so now we have this extra one, and let's quickly train a model. But before that, we just want to note time down, time.time, and then model CNN.fit, train images, train labels, epochs, Stren, match. Already. So just one additional point here is batch size, which is basically we didn't pass this in the ANN, but it's good to have batch size, because the more your batch size, the larger your batch size, the better your test performance, right? So we can actually start testing, and you'll see that it takes a lot of time. But in that time, we can obviously get the losses, and we can dot evaluate 8 test images and test labels. Yeah. So basically, I knew that this would take a little time, and that's why I kind of already have like a metric drawn below here. So I hope there are no questions. If there are there any questions about any if you didn't get any step properly or something like that. But before that, maybe I think we should draw this conclusion. Let's have a good conclusion comparison between ANN and CNNs, right? Since we're using the same loss, our losses are actually comparable in this case. So in this case, in the ANN's case, only neural nets, we have 0.33, and CNNs is lower, that's 0.24. The accuracy is 88%, and with the same model that I coded before, I had like 91%. I know it's not a big jump, but I'll get to how can we get that big jump. Now, the other part is that the computation time is 41.39 seconds. That is basically 4 seconds, because this is for the entire epochs, entire 10 epochs. So this is basically 4 seconds per epoch. And at the same time, it's 10, it's like a magnitude above. And this is not even a deep network yet. I mean, like, you can increase the number of blocks to like 10, 20, and that's when it's actually deep, right? So basically it takes 41 seconds, 10 times more. And that's why you need GPUs, and uh, it's out of the scope, out of this workshop scope to use GPUs. But basically, if you use a GPU, these times would be comparable. Like this would maybe be 50 seconds, or maybe even 41.39 seconds. Who knows? Um, so yeah, the trick is that instead of using just 2 blocks, we can have many more blocks like this, and actually our accuracies can reach like 96%, 97%, and so on. So so any questions? Do we have any questions?
Yeah, can you go back to the metrics part of the CNN, which was like above, like
Oh,
on
oh yeah,
this?
sorry. You mean,
Yeah, there. Yes.
yeah. So what was the question?
I'm getting an error that says invalid keyword arguments in compile optimization. And it's pointing out the metrics line. I'm not sure what it is.
So I don't know, maybe it could be using metric instead of metrics. Is that possible? Is that a possibility?
No, metrics, yeah.
Yeah, sorry, I had to go a little fast because we were a little low on time. But yeah, I guess it's easy, so it's not that big of a problem.
Yeah, it's probably just some like spelling thing somewhere.
Yeah, possibly you could just like debug that. But it's pretty simple. These modules have made training very simple, and
May I have missed out on a comma? I think I made a same mistake over there.
yeah, it's possible. You need comma between all the arguments, that you give to the function.
Also, I think to the question by Anthony, you just go to runtime and change your hardware settings to get the GPU.
Oh yeah, and but you have to also have a little bit of extra code to mention that you're actually using GPUs, uh, which you can definitely look at like Kera's page and all. So you've got the basic right, and the most important part is how to design your models. And once you are able to do that, the rest is basically just secondary things, and you'll get it like with just one look at the on the web page or on the documentation, and you'll get how to use those. But the major part is how do you design these models and how do you train them. So you can see it's still not over, but yeah, basically the session is actually over, and you guys could like leave if you want, but if you have any questions, please feel free. Oh yeah, so yeah, thanks for coming. So basically what from logic does it is so when you say it's from logic equals true, that means you're basically saying that you're not applying a softmax here. So if I were to remove this softmax here, and if I were to make this true, they are equivalent. So this is softmax. So this is from logic equal to. You're saying that you are not applying softmax before passing it to the loss function. So this is equivalent to having an activation saying having an activation of softmax and then applying simply the loss on it.
Alrick, if you don't mention that line from logits equal to true, does it treat it as from logits equal to false as default?
The default is true. Sorry, the default is false. Yeah. So you'll have to apply a softmax and pass it to it.
So when you mention in the dense part that cnn.add dense, if you mention softmax there, do you really need to mention from logits equal to false? If
Yeah.
from
Then you don't need
logits
to.
equal to false is a yeah.
Yeah, you don't need to mention it, but just so that like I have that argument and like I can have a discussion on it. I wrote it there, but yeah, you don't need to.
Oh, okay. Okay, thanks. And can you explain this dropout again? What does the point to mean?
Oh yeah, correct. So let's actually look at an example only. So suppose you have a matrix, uh, say 10, 20, 30, 40. So when I apply a dropout on this A, let us name this A. So what is going to happen is it's going to look at every element in A, right? And it's going to say that it has a 0.2% of probability that it's going to turn it into 0 or not. So basically it's going to look at 10, right? It's going to look at 10. It's going to generate a random number and between 0 and 1. And if the number is bigger than if the number is smaller than 0.2, then it's going to convert 10 into 0. So suppose it generates a random number and the number is below 0.2, so it'll be giving it 0. And for 20, suppose the number is greater than 0.2, it's going to keep it the way it is, and so on. So maybe for 30 it generates a number greater than 0.2, and for 40 it doesn't generate a great number than 0.2. So this is purely random. Does this
Okay.
make it clear? Or
So it just
Okay.
updates, like to add on to that, it basically updates the weights with that probability. So here it's keeping those things, but in an ANN, like it would either choose to update a weight or just ignore it.
Okay, got it. Thanks.
So this is done to avoid overfitting, which we were like talking in the last session. So if you don't, the dropout is like the simplest thing which you can use to avoid overfitting. So when a model is overfitting, it is essentially learning the noise associated with the data set instead of learning the actual physics or the relationship between the inputs and the outputs. It's learning the particulars of this specific data sets. So dropout is a really, really simple thing to avoid overfitting. And I think there was a lot of outrage recently because Google decided to patent it or something, and people were furious about that. Okay, so
So,
yeah, so that was
how,
the ANN model which I used. I think Jack asked.
Uh, yeah, basically, like,
how,
y- yeah, sorry. Does anyone have a question?
yeah, how do you decide that point two value? Can you put any value over there?
It's like, these things are very, what do you say? They're known in the industry. So it's like point two is like a famous value that you put. Similarly, there's another one in the optimizer called as momentum that's always 0.9. So you don't, it's like some guy has
Oh,
done
okay,
the
it's a
effort
fixed value,
and found out the good values and you
optimum
just
value.
use them. Yeah, yeah.
Okay.
We
And
just know
yeah,
that they are
surprisingly they work.
likely to work. So
Yeah. But yeah,
you
you
could
can,
totally
you,
optimize it if things are not looking good. You could maybe
yeah.
try it with like 0.3 or like go a bit higher or lower, or you could add it as a hyperparameter and start optimizing this parameter. So
Mm-hmm.
Yeah. Sahil, can you answer the ANN design question?
oh yeah, so this is so beautiful, right? Like you can just build the whole complicated network using just three lines. So you have an input layer, a hidden layer, and an output layer. That's it. So you are basically, so to construct an ANN, you are saying you begin with the sequential keyword, which, like Alrick said, this is basically saying, okay, so here is a list of layers and just put them together. You'll begin with the so tf.kras.layers.flatten. So the keyword is flatten. So flatten essentially takes the input shape. So if you have an image which is like 28 by 28 pixels, so this is a two-dimensional image. And if you see the ANNs, they are like a, so every ANN's input layer basically is like a one-dimensional thing. So you can use multi-dimensional data sets, but when you are training the ANN, you essentially want to convert it from two dimensions to one dimension. So flatten essentially does what it seems like it would do. So it would just flatten a 2D image. It would just compress it to one dimension. So if you have like 28 by 28 pixels, it would be a one dimensional 28 into 28 values, whatever that would be, like around 900 values or something. So this is essentially taking each pixel as one input. And in the next layer, you're basically constructing one hidden layer. So you have like 128 neurons, and you are saying use the ReLU activation function. And finally, you are saying I have 10 categories, so I would like to have 10 outputs. And I want these outputs to be fully connected with the previous hidden layer. So to say it is fully connected, you just say dense. So dense means like each neuron between the hidden layer and the output are connected. That's it. So does it clear like how it is structured? Also, we could totally send out this collab notebook for you guys to play around, or like start varying the weights and see how the efficiencies might vary and so on. Okay, and I think we'll send out the last feedback which you guys sent us was like really helpful in like changing things up and having the live coding session, since you guys thought that would be more useful. So please fill the survey again and let us know what's working this time and what didn't work, so we can make those changes and get back to you in the third session. Ah, awesome. The comments make me so happy. Okay, so I guess if that's it, like Alec, do you have like any closing remarks?
No, yeah, let's just fill the comments. That's it. Sorry, fill the Google forms. It'll be helpful for us to get feedback. Um, that's it. Yeah. Cool. Then, thank you so much for joining, and it was a wonderful experience for us as well. Thank you, and see you in the next one.
Yeah, I'll see you guys.